All right, thank you. Thank you for joining us for this discussion on high-performance computing. This is my last introduction. This is my sixth introduction, so I'm hoping I'm real good at it. I see Allie and Andy back there, so who already introduced already, so it's all good. But I'm J.C. Caesar with NetApp, and NetApp is honored to be a supporting partner of AppScia's TechNet Cyber. Our panelists will explore how cloud-based HPC can optimize workloads, accelerate innovation, and reduce hardware limitations. I hope that's what you guys are prepared to talk about.
Oh, yeah.
Good. As the intelligent data infrastructure company, NetApp partners closely with NVIDIA and other partners to provide AI-optimized flash solutions, whether on-prem or in any cloud, with unique advantage of having a single operating system and interface regardless of the cloud providers. Our speakers and panelists for today is Zachary Funt, Mr. Jeremy Lane, Forrest Hollyfield, and our moderator is Jerry Newell. Mr. Funt is DISA's technical advisor for the hybrid computing line of business. He provides guidance on cloud, automation, high-performance computing, and cybersecurity. Prior to DISA, he supported General Dynamics Robotic Systems and also administered systems at Johns Hopkins Applied Physics Lab. Mr. Lane is also a technical advisor for DISA Hybrid Cloud Computing line of business. Prior to DISA, he was a technical trainer for the Aegis program. I think that's the Aegis Weapon System program?
Yes, sir.
All right, good. Good surface Navy guy like me.
That's right.
Mr. Hollyfield is a senior technical advisor to DISA J9, overseeing cloud initiatives and large-scale infrastructure projects. He has been an automation PM on JWCC and a cloud ops technical lead. And Mr. Newell is senior technical advisor for hybrid computing line of business. His expertise spans IT project management, cloud computing, cybersecurity, and database administration. He began his career as a computer programmer for the U.S. Army. Please join me in welcoming our distinguished panelists.
Thank you, Billy. Appreciate it.
You got it.
All right, thanks, JC. Can you guys hear me okay?
Yeah.
All right, so as JC said, we are with the Hack. So our main goal is to provide hosting and compute for our strategic partners. So in that realm, we want to make sure that we are offering our strategic partners the capabilities that they need to support the mission, support the warfighter, and get down to business. So I'll be passing questions over to our panel here, and then after that, we'll open up questions to the field out there. So I'll just kick it off with Mr. Jeremy Lane. Can you give a high-level overview of what HPC is and why it's important today?
Yeah, no problem. So, what's the problem that we're trying to solve with high-performance computing? Think back to a normal server environment where you may have an application sitting on a server, and you may have multiple processes that need to share information. Normally that would be done in shared memory or semaphore on a single server, and that's confined to that single server, right? But if you wanted to use more compute or grow those resources, even with a hypervisor that virtualizes that and you can scale, even that has limitations, and that's still confined to a single VM. So how do you distribute your processing across multiple nodes, right? So if you've got one server where your processes are running and you've got that compute power and it's confined to that, but you've got 4 or 5 other servers, like how do you combine that? How do you utilize that? So message passing interface, or MPI, kind of enables that. That's a standardization that that people can develop their programs for distributed memory programming, right? So when you have 2 processes, for instance, and they're sharing that same memory, and they need to access that same information across multiple nodes in parallel, that's what HPC enables, not just from the processing standpoint, but all of its components, which I think you'll hear more about today. All of that, so every process has to share that data or read that data from storage all right? And same thing with the networking components. All that has to support that high throughput and efficiency that's required for parallel processing across massive compute inside of an HPC cluster. So distributed memory enables parallel processing to occur, right? So that's what HPC is doing. And what that does is it enables us to analyze large data sets, very quickly. So whatever those problems are, whatever that data may be, whatever the mission may be, it takes what would normally be serial processing and taking a long time, and you put that onto high performance computing, and now you have parallel processing, and that large data set gets analyzed very quickly, and in that case, supports the mission. So,
Yep, thanks, Jeremy.
thank you.
Zach Funt, what are the main components of an HPC environment, and how do they interact?
Thanks, Jerry. Before we move on, I did want to point out that you'll see some reoccurring themes with HPC. Jeremy had mentioned high throughput as well as vast amounts of data, so stay tuned. HPC mostly consists of 3 main hardware components. We're looking at compute, networking, and storage. Inside the compute, we have, it consists of clusters of computers, also known as nodes. These nodes, there's several types. I'm going to point out controller nodes. Several vendors call them by different names. But we're going to go with controller. They can serve as entry points for users for login, or they could underpin cluster services. We also have regular compute nodes, and these are the workhorses of HPC. They execute the computational tasks. We also have what's called specialized data management nodes, and these are designed for some efficient data transfer between nodes in the cluster, as well as they can also serve as ingress or egress to archival storage. So in short, with these nodes, the worker nodes or compute, they execute the actual computations, where the controller nodes manage these essential services and coordinate the work of the cluster. So our second component is, I mentioned, storage. So as it says, it's dedicated to storing and retrieving these vast amounts of data. The data that is generated and computed by the compute resources. Generally, the solution must meet a very high demand for this parallel distributed throughput, as well as some enterprise-level redundancy. Can be a physical on-prem solution. We also offer a hybrid cloud-based solution. There are several vendors out there that are currently providing the top tier throughput that we need, as well as compatibility with the cloud storage standards, which is essential. Our third hardware component I mentioned was networking. Networking is one of the most crucial parts of HPC. It's used for connecting and facilitating communications between the nodes. This typically, again, requires our theme of high speed, low latency connections to ensure the rapid data transfer between the nodes. And something I didn't mention, because it's not hardware, we have a software component, workload manager or a scheduler. This is designed to direct task requests from users, as well as managing the overall allocation of resources. So, in a fundamental sense, these compute nodes run the algorithms and software in parallel, doing that parallel processing over a pool of CPU, GPU, memory, and other resources. And this is all just interconnected through a network and linked with the storage, back-end storage. Thank you.
All right, thanks, Zach. All right, Mr. Forrest Holyfield, What types of applications are best suited for an HPC environment?
Thanks, Jerry. First of all, I just want to say that HPC, we're really excited to be getting into it. We found that there's a gap that we feel we can solve. I'm not going to go too deep into that out the gate because I'm sure it'll all get covered in further answers during this session. But what I will say is to understand what types of applications you find in HPC, you really need to think about what type of problems that it solves. And the types of problems that it solves are the most complex problems. Think of problems that span across science, engineering, business. Think huge amounts of data, having to compute extremely quickly across that so that the jobs that you're running ultimately get done inside our lifetimes. That's the kind of scale that we're talking about. It typically does this by running jobs in parallel, which is something that Jeremy touched on earlier. So it ultimately takes the tasks, breaks them into smaller pieces, and runs those concurrently so that it can compute as quickly as it can. A lot of times you'll find HPC in several different types of research. Think drug discovery, climate modeling, aerodynamics. Think about building airplanes, or designing airplanes, designing cars, those types of things that require a lot of simulation and modeling. It also is being increasingly used in artificial intelligence and machine learning, financial risk analysis, simulations, as I was saying, as well as media rendering. So there's a lot of things that you use almost every single day that at one point or another make its way through HPC in order to provide something to you that's valuable. So when it comes down to it, whether you're forecasting the weather, finding new materials, or analyzing DNA, HPC helps you get those results faster and much more accurately. Thank you.
Thanks, Forrest. All right, we'll go back to Jeremy. And so we've heard of CPU and GPU so far. Jeremy, can you explain what the differences are with CPU and GPU in an HPC server infrastructure?
Sure. So with the CPU and GPU, they're built for two different things, right? So one is general purpose serial processing, and the other is for parallel processing. So that's the big difference too. So I'm going to give a good example. One of my favorite examples of how CPU works is if you see these lights, for instance, these lights run on AC power. So anybody know what AC power does, right? It goes off and on, but if you look at the lights, it looks like they're on all the time, but they're not, because that's how AC works. But with CPUs and serial processing, right, when you look at your laptop and you look at all those processes that are running on that laptop or server, for instance, and you see all of those processes running, it looks like they're running at the same time, but they're not, right? Because they have to share those threads within each core of that server. Let's just say you've got a 32-core laptop. Well, that's, 2 threads per core, but only one could be active. So that's really about 32 threads. So I'm leading to an example here to really kind of put in your mind's eye the power of high-performance computing, right? So CPU, 32 cores, probably 32 threads, right? And now we move over to GPUs, right? And I'm going to give you an example. For instance, GPUs, parallel processing. And NVIDIA H100 has, about 16,000 cores, and each of those cores probably over 2,000 threads. And if you do the math, that's over 34 million threads that are processing in parallel, right? And it's just built for that. So that kind of power that HPC provides for answering the problems like Forrest had mentioned, taking those large complex data sets of those simulations, that's what it's made for, right? So CPU, it has its purpose, general purpose, probably running the operating system, and then you may have certain applications like stuff that runs simulations where it may need that kind of power that GPU provides, but they both have their purpose, and thank you.
Thanks, Jeremy.
Yeah.
All right, we'll go back to Zach. And Zach, you mentioned the network earlier. What role does the interconnect play in the HPC performance?
I'm glad you asked, Jerry. Actually, the I mentioned networking. The networking aspect of HPC is actually very fascinating to me. I've been down the rabbit hole before. I'm really interested in the technology and the topology of networking in HPC. So I'm glad you asked that question. Really am. So when we talk interconnect, we're really talking about the cabling and switches that are facilitating this communication between the various nodes. Simply put, it has a pivotal role in the overall performance of a high-performance computing cluster. There's several sophisticated interconnect technologies. Generally, most are equipped with some sort of intelligent offload engine. This reduces the processing burden on the CPU, freeing it up for computational tasks, thus improving the performance in a cluster. We also have access to remote direct memory access, or RDMA technologies. This is a zero copy technology. Basically, we're bypassing the kernel here, where the network adapter pulls directly from application memory and sends it right on the wire. So high speed, high bandwidth, low latency. You'll see this mostly in InfiniBand technologies, can be not as cost effective as others. So we further evolved to this RDMA technology over converged Ethernet. If you're an acronym guy, I really like this one. It's Rocky, capital R, little O, capital CE. If you repeat it 10 times, I hope it catches on. But Rocky. So in hopes here, we're bringing this RDMA technology to converged Ethernet, in short, to hopefully bring the costs down, make it more cost effective. And then lately, we're seeing more of the Ultra Ethernet. This promises to fix everything. In short, it'll fix everything. At least if you do the research, they claim to have better congestion control, security built right in day one, and better loss recovery. I'd also mention I'm really interested in the topologies. I don't think we have time today to explain them, but pretty common. We see fat tree, as well as the dragonfly topology, which I also find very, very fascinating. I'm telling you this because these modern workloads, like AI, ML, machine learning, they demand more bandwidth and lower latency. So we're going through this continuous modernization phase with these technologies, where they're introducing new technologies like this adaptive routing, like I mentioned, RDMA over converged Ethernet. Basically, more features that deliver the required performance of these modern workloads. But ultimately, the selection of interconnect technologies and topologies, right? They depend on the specific needs of the application or workload, as well as budget constraints of the strategic partner and the overall system setup.
All right.
Thanks.
Thanks, Zach. So the next question we'll take with Ms. Forrest. So typically, if you're familiar with hosting and compute, you normally get small, medium, or large-sized OSs. So Forrest, can you explain how workload sizing is aligned with configuration and performance needs?
Yeah, thanks, Jerry. And this is a question that comes up pretty commonly with our strategic partners when we have engagements with them. So it's something that we're used to. With HPC, typically you don't get the standard T-shirt sizes that we've all become accustomed to, especially when you look at how the commercial cloud providers over the last few years have used that, standardized on that, and have ingrained that in us. For the more commodity hardware, what we're doing with HPC and the way HPC workloads typically work, you don't typically see that. With HPC, the what you get is more tuned to the problems you're trying to solve, the jobs you're trying to run. and going down that direction. And ultimately, what it comes down to is compute. So how much and what type of compute? And when we say what type of compute, with the emergence of AI, ML, and going more, away from CPUs to GPUs for certain type of task, that's what we mean when we say what type of compute. And the GPU has made its way into the HPC workspace as well, and is becoming more and more prevalent because it solves a lot of problems. So talking about that, you can have different sizes of jobs. You could have small jobs that are 1 or 2 cores. They could finish in seconds or minutes, to where it could scale all the way up to where you have thousands of jobs that are very large jobs that go across thousands of cores that can take days or even weeks. That's the kind of scale we're talking about here. Another thing to consider is, as your workload grows, so do your memory requirements, your storage requirements, as well as your networking requirements. So it's important that you match your hardware to the job you're trying to run to ensure you get the performance that you need out of that job, as well as making sure that you're not wasting resources, and ensuring that your HPC cluster you're using it in the most efficient way possible. So you need to know your job needs and make sure you're configuring the systems properly to handle that.
All right, thanks, Forrest. You mentioned a lot of things about jobs in there. So, Jeremy, what does the HPC admin experience look like in terms of jobs, monitoring, user quotas, and queue management?
Yeah, no problem. And just to talk about what Forrest just said, when you have jobs that could run days or weeks, and you could have anywhere from 100 end users to 1,000, managing a cluster like that, how do you keep it up to date? How do you manage those end users, what they're doing, and the quotas, right? So an HPC admin, you're responsible for the daily operation, the maintenance, and the support of that cluster. And the majority of that is, the end users and making sure their jobs run interrupted and without issue. But you also have to balance that with, the security requirements and the updates that are required for those compute nodes or those login nodes that could affect those jobs, right? So how do you balance both of those? And the scheduler is kind of key with that. You can assign end users to queues, and then inside those queues, you can partition out those kind of resources. And between that, the way you build out the login node and the partitioning piece, you can manage those jobs that are ran or scheduled, and those end user quotas to kind of balance the operations with the maintenance side of HPC. So as an HPC admin, that would probably be your normal everyday experience.
All right, thanks, Jeremy.
Yeah, thank you.
All right, speaking of scheduling, let's go to Zach. How do tools like Slurm or PBS improve workload scheduling and management?
Thanks again, Jerry, for an amazing question. So these workload managers that you mentioned are fundamental to the efficient operation of high-performance computing. They're fundamental because they automate the scheduling, the dispatching, as well as the overall orchestration of these computational jobs. They generally offer a suite of features that are designed to optimize the utilization of the compute resources on the cluster and streamline the execution of user jobs. They, in a way, provide a sort of a load balancing capability. What I mean by that is they ensure tasks are distributed efficiently across the nodes. By preventing. I can't read my own writing. Sorry. By preventing any single node from being overloaded, while at the same time other nodes from being underutilized. There's various advanced scheduling algorithms that allow for the submission of jobs with specific resource requirements. You can request the number of CPUs, GPUs, the amount of memory you need, as well as the max execution time of these jobs. They're all managed based on availability and priority. So, as we sort of mentioned the interface here, the users interact via job scripts, which are basic text files that specify these job requirements that we just went over. There's also several command line tools that are for submitting, monitoring, and managing these jobs. We also have some advanced features that further enhance the workload management. We have there's a concept, job arrays, that are groups of multiple similar tasks that act as a single entity, as well as options for job dependencies, which I think that's really neat. You kind of create a workflow enabling the creation of these complex workflows where these jobs execute in a specific order, as well as an advanced reservation system where you can reserve resources for future use, and fair share scheduling policies where resources are allocated equitably among separate users and groups. This certainly isn't a complete list of features for these schedulers. What I'm trying to get at here is that these modern schedulers are basically acting as a distributed operating system of sorts for HPC.
All right. Yep.
Thank you.
Zach. All right, Forrest. How does the system handle containerized applications and orchestration?
Thanks, Jerry. Yeah, so containerization, obviously, super popular and is only gaining in popularity. It's been around on the commodity hardware side for a very long time. You've probably heard the term cloud native. It's not exclusively that, but it can be a very big piece of that. And so, now it's starting to make its way more and more into the HPC world as well. What containers can do is simplify running your applications. There are tools such as Singularity and Apptainer that can package software and dependencies into a single image and allow you to run those across multiple different environments with the same results ultimately. So makes it very portable and easily to move around and different places. We've heard the Slurm scheduler mentioned several times up here. So the Slurm scheduler can also run containers and manage their resources, although that's not necessarily its bread and butter. Now that containers are becoming more and more popular, well, actually, let me go back to Slurm real quick. So yeah, so Slurm, since it's not necessarily for Kubernetes, it's not necessarily for running containers. Like I said, it can. What it's good at are those traditional batch jobs, and we got a little bit more detail about that from the other two guys up here. But now in HPC, it's starting to venture into that Kubernetes world a little bit as well. And what that ultimately does is it allows for more dynamic as well as more complex workflows in your HPC environments. So what it comes down to is containers make it easy. They allow you to run software more reliably, manage dependencies better, and create repeatable environments so that you can run your workloads in a fashion that is a lot more consistent.
All right, thanks, Forrest. All right, so this is my favorite question for Jeremy. Why should an organization consider DISA for HPC solutions?
So it's probably the favorite question today. As you guys have heard so far, the HPC environment can be pretty complex. There's a lot of complex infrastructure, the networking, the storage requirements, the nodes, the management. There's a lot of cooling and power requirements, right, that go into the cluster itself, and there's a lot of overhead and resources that are required to manage that cluster. And so you can offload that with DISA because we're experts in infrastructure hosting and operations. We provide global infrastructure and robust communications across the DoD. So you can focus on the mission. We have enterprise services, labor services, capacity contracts that keep that hardware up to date. We monitor the hardware support, the firmware requirements, so you don't have to worry about any of those things, what's supported. You just focus on the mission. You can log into your HPC cluster, execute your applications, and with peace of mind and knowing that it's done in a secure manner. So we're also, an arm of the DoD. We're many of us have served before. We're now in civilian clothes. We're all family, and been a technician with DISA since 2010. Right, so I can tell you that no matter what the mission is, no matter what the gap is, that we all come together in that digital foxhole, whatever it may be, for whatever the mission, and we're going to close the gap. So you don't have to worry about the hardware, you don't have to worry about the infrastructure or the data center, but we're there to help you focus on the mission. Thank you.
Thanks, Jeremy. Zach, how does DISA's approach simplify HPC deployment and scaling?
Again, I'm very glad you asked me that question. So DISA's approach to providing HPC solutions has several key initiatives here. These key initiatives are aimed at simplifying the deployment process as well as scaling of the critical resources in HPC. Our strategic vision includes establishing a resilient and globally accessible hybrid cloud environment built on DevSecOps principles and capabilities. This direction indicates a commitment to provide a more flexible and automated infrastructure that can adapt to the evolving needs of the Department of Defense. DISA is actively working towards a standardized, homogeneous IT architecture that's expected to reduce not only costs but complexity. Today, DISA offers a comprehensive ecosystem, not just of hardware and software, but that critical networking and storage infrastructure, as well as IT expertise that simplifies our deployment process for production workloads within the Department of Defense. DISA is your one-stop shop for hybrid cloud.
Thanks, Zach. All right, so the last question for the panel. Jeremy, how is customer experience being redefined in the context of HPC?
Thank you. So how many of you were here on the first day for Mr. Barnhurst's keynote speech? You guys remember the example that he gave with his grandfather being a forward observer? Right? No. So he talked about his grandfather being a forward observer, and during a particular mission, they spotted the enemy. And looking at that enemy, they had to take, or his grandfather had to take the information that he had, analyze that data quickly, right, so they could execute and get rounds on target before the enemy could. So I want to tie that back into what we're doing with high-performance computing, because originally it wasn't in my answer, but after hearing that, it was a great opportunity to talk about what he said and tie it into the way we used to manually process complex data sets, right? So think about it as a forward observer. You know, you've got how far are they located, what's the wind, the temperature. You've got all these things that they would have to take in to account. Well, going back to what Zach said, that through simulation data or modeling, that information can be provided very quickly. All right, so that enables us to get the right data to the right place at the right time, right? And for the commanders to make better decisions better and faster than the adversary, which is exactly what Mr. Barnhurst's grandfather was able to do manually. But now we've got high-performance computing to do that. So as an example, today, no matter which web engine you may use or provider you may use, you may search something, and at the very top you may see a concise summary. How many of you guys have seen that now when you search something on the internet and you see that concise summary? So before that was there, you may have 1,000 results, and then you may have to go into those 1,000 results and manually look at all that information, pull out what you need, and then build that answer. But now, when you type in that question, you've got something called generative AI producing a concise answer quickly and efficiently using all of that complex data that's being pulled in across the internet. And that's what HPC's doing for us, especially in our environment and with the mission. It enables us to get the concise answer that we need quickly to beat the adversary. And in that case, it's going to be key in enabling lethality for our missions.
Fantastic. Thanks, Jeremy.
Yep, thank you.
All right, that concludes our questions. Let's go to the audience. If there's any questions out there. Adam?
Hey, Rocky for Zach. And then, great brief. I really appreciate it. In your experience and what you've seen so far from the demand signal for HPC, are you starting to see more of this turn from the research laboratories and start coming to DISA? And what is DISA doing that is providing the service to that strategic partner so that way they don't need to necessarily stand up their own HPC within their data centers?
Do you want to take that?
Yeah, Jeremy, go ahead.
Sure. Yeah, as a matter of fact, we have had some conversations with the Army Research Lab and the HPC MP and what they're doing out there for research and development, especially out there on the Dren. And so what we want to do is we want to be a landing, like I said before, we're experts in infrastructure and hosting, right? We know the RMF, right? We know the framework that's out there. We know the computer network defense. We know all those things to take something and put it into a production environment and do it in a secure manner. And so at a point to where you might be ready to take something that's, research and development and actually put that into an environment where you want to actually use it for a particular mission and give access to a warfighter, that's what we do, right? So we can partner with those kinds of customers that may be out there right now in a research and development format where that may not be suitable for them once they've kind of outgrown that environment, and we could help them land into an environment within DISA to be production ready.
And follow-up question, what's the best way for our strategic partners to get in touch with you all so that way you can provide that service to them?
I'd say the best way for strategic partners to reach out to us is to go through our hybrid cloud broker. They're located right over there.
Yeah.
So yeah, you can go over there, you scan the QR code, and it'll take you to the website to hook you up with my man over there, Brandon Glover. Any other questions?
Hey, how's it going?
Alan?
I was curious, is it just located at one location in one data center, or do you guys have this system in several different data centers? And then are you guys also reaching out to other DIS entities that are running C2 systems like GeeksJ, JOPE, JPAS, to see if maybe those other DIS entities that are supplying that battle space COP to those individual commanders on the battlefield are interested in leveraging the same kind of technologies?
So,
Good.
yeah, I'll try to answer that the best I can. So, as you probably heard throughout this panel session, HPC is kind of complex, and there's a lot of dependencies that are out there, right? You could have a small cluster, you could have a large cluster, depending on what servers you want to run, what type of processors, what type of GPUs. Your power and your cooling could be different, so you may want it in one environment versus another. We may have one data center that's more suitable for that than another. Again, like I said, we have data centers across the globe. And what we would do is we would probably work with you through our hybrid cloud broker team to set up an initial meeting to really get an understanding of what your why is before the what, so we can find out what those requirements are and build out a solution that fits you best, because it's always unique to whatever your mission may be, right? So one data center may not fit the requirement just like another, so it's always about getting the details that we need to give you the best solution.
Thanks, Jeremy. Any other questions? I know you guys are just waiting for the happy hour. All right. No other further questions. I'd like to thank the panel. Thank you, guys.
Thank you.
Thank you.